Hello and welcome back. Let's look at one final example on the normal approximation to a binomial distribution. So here we're going to find the probability of rolling at least 25 sixes when rolling 100 dice. So again, when we're rolling 100 dice, each time we roll a die, we have a chance of succeeding in rolling a 6 or failing in rolling a 6. So this will be a binomial distribution. The probability of rolling a 6 will be 1 out of 6. There are 6 sides to a die. The probability of not rolling a 6 would be 5 out of 6, rolling any one of the other 5 sides. So in order to use the normal distribution, we need to know two things: the mean and the standard deviation. So for the mean, we're going to use the binomial mean and just treat it as a normal mean. So this is going to be n times p, which is 100 times 1/6, which is equal to 16 and 2/3. So just write it as 16.6 repeating. And the standard deviation of a binomial distribution is the square root of n times b times q. So this is, if we fill in all these, this is going to be the square root of 100 times a sixth times 5/6, and this will be approximately equal to, I had this written down, 3.73. Now, I'm going to leave this as exact when I'm calculating the z-scores in a second, so let's think about what exactly we want to do. I can draw a better straight line. So we want the probability of rolling at least 25 sixes. And with our mean of 16, don't want to do that, 16 and 2/3 sixes, 25 will be somewhere over here maybe. So we want the probability of rolling at least 25 sixes. However, we need to keep in mind that we have a continuity correction to this. So when I say 25 sixes in a binomial distribution, in the normal distribution, what I mean is anywhere from 24.5 to 25.5 sixes. So we'll need to look at what it means to roll at least 25 sixes. And I think the easiest way to think about this is we need to include 25. At least 25 could mean 25, 26, 27, 28, and so on and so forth. So when I'm thinking about within the normal distribution, what does at least 25 mean? Well, I have to include 25. I have to include the next number, and the next number, and so on and so forth. So at least 25 sixes. When I'm looking for this probability, what I really want is the probability that x is greater than or equal to 24.5. And again, I want at least 25 sixes. So 25 is at least 25, so I do want to include that. So I need to start at 24.5 and go up. So the next order of business will be to normalize everything. I shouldn't use that word, to make everything the standard normal distribution, where the mean is 0. So I need to find the z-score for 24.5. So for the z-score, we take the number itself, we subtract our mean, which when I input this into calculator, I'm going to leave everything as fractions so that this is more precise and I'm not rounding and then rounding again and rounding again. And then I need to divide by the standard deviation, which would be 100 times 1/6 times 5/6, the square root of all that. And this is now approximately 2.109. So we can come back to our StatCrunch, and now we want the standard normal distribution. We want to see the probability that x is greater than our number, which is 2.1019. So our probability is going to be 0.0177, or I'll round that to 78. Oh, and it looks like I wrote this wrong here. So our probability from our z-score on, let me fill in this z-score here, is equal to 0.0178. So this is the probability of rolling at least 25 sixes according to the normal approximation of the binomial distribution. So this event, for instance, is less than 5%, so it's less than 0.05. So if this were to actually happen, this would be a significant event, and I might be led to believe that maybe the dice was not fair. One thing that we can do is, if you come back to StatCrunch, there is actually a calculator for binomial distributions. So let's look at the actual value, because remember, this number is only an approximation. We're assuming that the binomial distribution is like a normal distribution, when in fact, it's not exactly a normal distribution, but it should be quite similar. So here we have a value for n, so we were rolling 100 dice, and the probability of success should be 1 divided by 6, and we want to look at probability of rolling greater than or equal to, which is at least 25. So the actual percentage is 0.217. So the actual value is 0.0217. So these are pretty close, and because we have the calculator, this would make sense to just calculate this directly. We're not in a situation that requires a normal approximation. However, there are situations in which the normal approximation is easier to use and will be quicker to use. The binomial calculator that we have is quite nice, but sometimes there may be situations where the normal approximation is a little bit better. And what you'll notice is that even with 100 dice, even having 100 trials, this is not quite the same. However, if we were to roll 200 dice, 500 dice, 1,000 dice, these approximations would get closer and closer and closer. So the approximations get better when there are more trials.